structs and unions and enums and whatever, and then safely perform file I/O. I think most of this, I think actually all of this should have been covered in 264, but that's sort of the like prerequisite level of knowledge that I'm going to assume. If there's stuff here that you struggle with or maybe anticipate struggling with, let me know and we can figure out a way to get you caught up. All right. So what I hope you will learn over the course of the semester. So we're going to talk about some basic data structures like stacks, queues, and trees. We're going to learn how to analyze the time and space complexity of both iterative and recursive algorithms. So this is stuff like big O, big theta, o, little omega, all of that. Kind of understanding what algorithms are appropriate to use in what situations. How to apply the appropriate sorting and searching techniques for a given application. So we are going to learn about both of those. And then my personal favorite towards the end of the semester, hopefully there'll be enough time for this, but some graph theoretic techniques, including some interesting graph algorithms. So hopefully we'll talk about stuff like, I don't know, Euler cycles, traveling salesman, graph coloring, max flow, min cut, that sort of thing. And then finally, just a generic, like given an engineering application or given like a lead code problem or something like that, how do you figure out the right data structure and the right algorithm to use for it? So hopefully you all will get some practice with that sort of thing. In terms of grading, this is kind of alluded to on the syllabus, but there's going to be problem sets, roughly one per week, and they're going to be worth 30% of your final grade. So there's not going to be one due right now, obviously, because it's the first day of class, but I'm going to release one this Friday, and then it's going to be due by the next Friday. So every week except for the first week and the last week, you'll have a problem set due. And those will be due on Gradescope by 11:59 p.m. You are free to like talk to your classmates about these problem sets, collaborate, etc. But I do ask that you write all of your solutions individually, and if you do collaborate with someone, just like write their name at the, or like list your collaborators. That way, if two people have like very similar answers or something like that, we can take a look at that and be like, oh yeah, they collaborated, so it's like it's fine. And finally, there might be a bonus problem set at the end of the semester. This kind of depends on what material we get to and whether I have the time to write one, but something to potentially look forward to. Each problem set's going to be roughly equally weighted. So if there's 6, then you can expect each one to be about 5% of your final grade. Next step, programming assignments are also going to be worth 30%. Currently, I'm thinking there will be 3 programming assignments. Tentatively, the first one's going to be something like building a window manager. That will be released this coming Monday, so a week from today. And then we'll do some kind of spatial indexing for the second one. And then I'm hoping to do something like solving mazes for the third one. Like I said, they'll be released on Mondays and they'll be due 2 weeks later on Gradescope at 11:59 p.m. So from Monday to Monday. That also covers the middle 6 weeks. There's 3 assignments, 2 weeks each. Yep, awesome. Programming assignments will be evaluated on 3 criteria. So first of all, there's correctness. So the way it'll be graded mostly is like we'll have an autograder up on Gradescope. You'll submit your code. It'll run it against a bunch of test cases, and you'll get like a certain number of points based on how many test cases pass. You will also be graded on memory management. So for every test case that has like a memory error or a memory leak, even if you get the correct output, you will get a 50% penalty on that test case. So theoretically, if you pass all the test cases, but half of them have leaks, you would get a 75%. And again, the autograder will like tell you about that. So hopefully there shouldn't really be any surprises as to what your grade is after the deadline. And then there will be, there's like a timing component, sort of. So at the very least, your program has to finish within a timeout, which is going to be something very generous, like 10 minutes. That's just to make sure you don't have like an infinite loop or you're not doing some ridiculous like combinatorial time solution that doesn't actually test your data structures knowledge. Later projects, we might have some incentives for faster time. So like having like cutoffs, like if you get above or if you get below a certain number of seconds and you get a certain number of bonus points or something like that. But more details about that will be released with the projects. So yeah, released on Mondays, due on Mondays. As you might have noticed in the syllabus, there's also the opportunity for extra credit with every programming assignment. So you can submit a write-up to Brightspace. This is mostly graded just based on like effort. You can get up to 10% extra credit if you document like, I don't know, cool stuff that you did. If you implemented something that wasn't in the spec, you can tell me about it. If you uh, talk about like the decisions you made and why you made them, stuff that you found particularly easy or difficult, stuff that you learned from a class or whatever. Um, yeah, so and that can kind of just be in any format, but that'll be due at the same time as the programming assignment itself. So yeah, extra credit. That's 30, that's 30. There will be two exams. There's a midterm and a final. Each is going to be worth 20%. I currently have the midterm scheduled for July 10th during class time. That's a Wednesday. It's going to be proctored via Zoom, so we'll like release a PDF or something on Brightspace, and you'll take the exam and then like scan it into Gradescope or something. We'll figure out logistics of that. And it's going to cover content from the first 4 weeks of class. Now, I do realize that there's a lot of people who are on like internship. Maybe none of you because you're here, but maybe the people watching the recording. And so in particular, I know that there's like conflicts with the first or like with this class time. Oh yes, DRC accommodations. Um, I will also I need to figure out how those work, but I will probably have a uh separate proctoring session for those. But yeah, if you have a conflict with class time in general or with that particular day, please email me as soon as possible and let me know because I would like to have as many if there's a bunch of people with conflicts, it would be ideal if we could all kind of have one proctoring session for everyone who can't make it to the normal class time. So yeah. Was there a question? No. Okay. All right. Great. So the midterm is worth 20%. The final exam is worth another 20%. It is also cumulative. It'll cover content from everything but the last week. So the last week we'll kind of do hopefully some extra graph stuff and probably some final review. The date and time for that is to be announced. I unfortunately do not have complete control over final exam scheduling. So once the powers that be let me know, I will let you know about that. Cool. So that's the exams. I'm just kind of going through the stuff in the syllabus right now. Late policy. I have seen this late policy implemented in the past. I really, really liked it. So I'm going to try it out again. All assignments, like programming assignments and problem sets, you can submit up to 5 days late. The first 5 late days that you use throughout the semester, there's absolutely no penalty. So you get all the points you would have gotten. This is like, I know summer semester, 8 weeks, it's kind of cramped. You've got internships and other stuff going on. I know stuff comes up. I know things happen. So you don't have to worry about the first 5 days you take. And you don't have to like email me or like let me know that you're taking a late day. You can just turn it in 2 days late and we will deal with the accounting on our end to make sure that you aren't deducted points for something that you shouldn't be deducted points for. After that, it's a 10% penalty for each day late. In particular, note that even if you have like enough late days saved up, you can't submit something like 10 days late just because we want to keep things on track and because I don't want to leave assignments open for arbitrarily long and then have to go back at the end of the semester to grade something that was due at the beginning of the semester. So 5 days late for each assignment. 5 days, the first 5 late days throughout the semester are free. So for example, you could submit the first programming assignment 2 days late and the second one 4 days late, and you would get all the points on the first one and then a 10% penalty on the second one because of those 4 days, the first three would have been your free days, and then the 10% would be the 10% penalty for the last one. If you submit on time, will you receive a grade? Uh, yeah. So you can resubmit. The way it works on Gradescope, at least, is there's like an active submission thing, and so after the late period is up, we will just look at whatever submission you currently have marked active and grade based on that, and grade based on the time that you submitted that. So in particular, if you submit on time but you didn't get a great score and you want to use up some late days to get a potentially better score, you can do that. And then if you submit late and you don't get a better score, you can just reactivate your old one. So you were sort of free to like, I don't want to say game the system, but like game the system insofar as uh setting setting stuff up on Gradescope, or like setting the active submission on Gradescope. You can submit to Gradescope as many times as you want. The Gradescope will have an auto grader built in. You will hopefully be writing your own test cases as well. And so you don't have to submit to Gradescope to see stuff. An ECE server with the same GCC version as Gradescope. Yeah, so I don't know if you all know how to access like ECE Prog or ECE Comp. I sort of assumed that you would, but if not, I will send out like instructions for how to do that. But yes, there is ECN does have a server that has the same like the same OS and the same GCC version, stuff like that. And so I'll send out I'll post something on Piazza with instructions on how to access that. But of course, if you want to develop locally, ECE Comp runs a version of, oh yes, ECE Prog I think should be more up to date. Yes, if you want to develop locally, you are free to set things up locally, as long as you're aware that in order to get points, it has to work on the version of stuff that we have set up on Gradescope. And again, details of that are in the syllabus. Cool. Any other questions about like programming assignment, submission stuff? All right. Yeah, okay. So that's the late policy. I am open to granting extensions. So if like something happens, if there's some extenuating circumstances, please do let me know. And we'll make sure that like submitting things for a class is not something that you need to worry about in those circumstances. So yeah, feel free to reach out to me about stuff like that. Resubmission opportunities for programming assignments. Yeah, so like I said, you can submit your code as many times as you want to Gradescope, until you get all the points you want. And Gradescope will give you some feedback on like how many test cases you failed and stuff like that. So there's no like submission limits. There's nothing like you can only submit once every 8 hours, you can only submit once at the end or whatever. You will hopefully get feedback within like a few minutes of submitting. So yeah, there shouldn't really be any surprises on programming assignment grades. Cool. All right, I'm gonna move on. Oop, I said I'm gonna move on. Am I? Ah, can I? Can I move? Wait, well, oop, yeah, there we go. Okay, perfect. Attendance. Again, this is sort of a the people watching this right now obviously are attending class, but there will be a recording posted. So I need to, yeah, okay, great. Attending class very regularly is important. I will be posting like the lecture slides and the recordings afterwards. But if you are here in person, I guess synchronously or whatever, you can ask questions and you can like engage with the material a lot better. So I highly encourage it if possible. If you miss a class, it is your responsibility to catch up on the material. I won't be after you to be like, hey, you missed this lecture, make sure you catch up. Like I said, I'll try to post slides and videos to Brightspace within a day or two of each lecture. I can't promise that it'll be immediate. And I will be taking attendance via periodic in-class polls. So this is something I listed on the syllabus as well. So this will be like during lecture, I'll have a question or two that I ask. There will be a Brightspace submission open for it. There is already a poll up for today. Yes, excellent. The question, I will ask a question in lecture today for attendance. The Brightspace submission will not have a question on it. So to submit a response, you do need to have watched the lecture. That is on purpose. because I'm grading this based on completion, not correctness. So like if you submit something, even if you don't know an answer and you tell me like a funny joke or whatever, like that counts. That's fine. I was gonna have it be until the end of lecture, but again, there's people who can't make it on the regular scheduled lecture time, so I'm gonna leave that open until the end of the day, 11:59 p.m. Eastern. And as you may have seen in the syllabus, you need a 60% response rate on the polls to pass, 80% to get an A. So that should hopefully be pretty straightforward. Oh, when I have the Zoom chat open, it captures all of my keystrokes, and so I can't advance slides. Here we go. All right. In case of emergency, Purdue tells me that I have to include this slide on my lecture. This is a remote class, so we don't have like a fire drill procedure or anything. Not much specific to see there, but there is all of the appropriate legalese on the Brightspace page. So you can take a look at that for details. Cool. All right, moving on. Our first in-class poll. Isn't everyone so excited? All right, what pair of functions can you use in C to dynamically allocate or deallocate memory on the heap? If you paid attention to like 8 slides ago, this was kind of alluded to there as well, but I don't care, like it's fine. For a bonus point that is worth absolutely nothing, how do you dynamically allocate memory on the stack? I'm going to leave that open for maybe a couple minutes. Also, feel free to like talk about it in chat. It's fine. Yeah, this is fun. You don't have to submit it right now. You can submit it by the end of the day, but I'll just leave that up so that people can. Yeah. So there's an assignment open for it on Brightspace. So it'll be under like modules and then like in class polls or so, like attendance polls or something like that. There'll be one for today. So you can just like write your answer there. Um, Again, if you don't know the answer, it's fine. I mean, well, actually, for this one, well, you should maybe know, but uh, in general, like this is just like based on completion. Okay. I'm hoping everyone who's going to look at that has looked at that. Cool. The answer is malloc and free. Yeah, we knew that. Um, oh, the bonus. How do you dynamically allocate memory on the stack? Uh, yeah, just write the answer in Brightspace and submit it. Um, okay, there we go. To dynamically allocate on the stack, there's this thing called alloc A. Do people know about this? It's kind of uh, it's kind of scuffed. It's pretty cool. You can allocate things. You don't have to worry about freeing it because when the function exits, like it cleans up its own stack space, and it's great. It's fun. It's also how like variable length arrays work. To attach a file. Oh, well, rip. I will. I don't know. Maybe you can upload like a blank text file or something. I'll figure out how to make that work correctly for the future, and also probably yeah, you can just write it in the comments. I don't know if it doesn't let you submit without attaching something, but um, yeah, I'll make sure to fix that next time. I haven't really dealt with Brightspace a ton, so um, yeah, good to know that it does that. Anyway, yeah, alloc A is pretty cool. Um, that's my that's my alloc A pitch for this lecture. All right, possible list of topics for the class. So again, this is mostly in the syllabus. These are mostly sorted by like week. So first week we'll be talking about linked lists, stacks, and queues. Some of this should be reviews, some of it might be new material. Next week we'll talk about time and space complexity, analyzing recursive algorithms, and something called the master theorem. Then we'll talk about sorting algorithms, merge sort, insertion sort, quick sort, and shell sort. You might notice heap sort is not on there, and that's because we're going to talk about heaps later. We talk about trees, so binary trees, KD trees, prefix trees, BSTs, balancing. Uh, Yeah, sure. You can write the answer in a text file. Um, yeah, trees, all kinds of trees. Um, everything's a tree. Well, a lot of things are trees. Then we'll talk about heaps and heap sort. Heaps are a special kind of tree that have particular semantics associated with them. We'll talk about abstract data types, hashing algorithms, collision resolution, and then finally my favorite, which is graphs. So like I said, we'll talk about Euler tours, traveling salesman, spanning trees. We'll talk about graph search. Graph search is actually probably more relevant than all the stuff in that previous bullet, so those might be flipped around. We'll do like Dijkstra's and ASAR. Uh, cool. Um, Midterm one will cover through heap sort, and then we'll start abstract data types after midterm one. So just so you have some sense of like what's going on. All right. My slide preview tells me that that is the end of my intro slideshow. So I'm going to stop sharing. Are there questions about that stuff so far before I move on to actual content? Oop, what? Oh, I know we kind of had questions in the chat as we were going, but is there anything left? If there's nothing, I will move on. Um, so as alluded to, the first topic is linked lists. I'm going to share my screen once again. Yeah. All right. I assume if people could see the first one, people can see this one too. Screen sharing hasn't broken itself in the past few minutes. All right, great. So, the first actual topic of this course is linked lists. Some of this might kind of be review, but if it is, it's good to have a refresher. If it's not, it's good to know because a lot of things we're going to be talking about are going to sort of somehow be derived from linked lists. So linked lists are going to serve as like a concrete way to implement a bunch of things. So as a warm up, there we go. All right, as a warm up, let's talk about arrays. Arrays are in particular not linked lists. Arrays are allocated in a contiguous blob of memory. You allocate them once, and then you just keep using them. So yeah, one allocation, one free at the end. Elements are packed very densely together, so like the next index is always like adjacent in memory. Arrays are pretty cool. So in particular, they're very good for the cache. If you fetch one element of an array, your operating system will often load the entire array into memory immediately, and so like accessing other elements of the array is pretty quick. Random access is really easy. So if I want to get like the 10th element of an array, I don't have to loop through 10 times. I can just look at the address of the array and I can do some like pointer arithmetic to offset that by 10 and then dereference. And then there's fewer allocations and deallocations, right? I allocate it once at the beginning, I use the array for its entire lifetime, and then when I'm done with it, I clean it up. Arrays are great. So why do we need linked lists? Well, in particular, inserting or removing from the middle of an array is kind of difficult, right? If I go here, I want to delete the 3. Oh, that's great. If I want to delete the 3 in the middle, I can like clear it out, I can zero it out, but then there's still like an element there. So really what I want to do is like get rid of it and then shift everything over, but that means I have to loop through the entire rest of the array and copy everything back one. If I want to insert something into the middle, first of all, I might not have enough space, which means I might need to reallocate a slightly bigger array and then copy everything over and then put the new thing in the middle. So it's a lot of work. Yeah, and then dynamically resizing is really hard. So like I said, even if I'm inserting at the end, if the chunk of memory that I've allocated isn't big enough for the number of elements that I want, I have to resize it, I have to copy everything over. And when we talk about like time and space complexity, we'll have some better words to describe that or some better language to describe that. But it's bad, right? That's not what you want to do, especially in like something performance critical. If you're like appending and deleting things from an array all the time, um, you don't want that to be the thing slowing you down. You don't want that to be your bottleneck. Um, okay. Instead, you can have linked lists. So with a linked list, instead of having things kind of uh, contiguous in memory, instead of having everything adjacent, each element just knows where the next element is. So instead of having like five things all allocated in the same space, I have a block here, and then it knows where the next block is, and it knows where the next block is, and these kind of can like just go all over memory. Inserting becomes pretty straightforward now. I can reroute through a new element. So if I want to insert this 4 between the 2 and the 3, I just have 2 points to 4 and have 4 point to 3. And now my chain remains unbroken, but now it's got that 4 in the middle. If I want to delete something, I just skip over the element that I want to delete. Of course, if this is like dynamically allocated, I have to free the thing that I'm deleting or whatever. But like semantically, this is sort of a lot easier, right? So that's the basic idea of a linked list. In C, how do we represent it? You can use a struct, right? So struct linked list node. It'll have two fields. One is a value. Here we've just assumed values are integers. It can be whatever type you want. And then it has a pointer to the next node. And so you can see a sort of linked list on the right here, where I've got three nodes. Each node has two fields. We've got the value, which is the number, and then we've got the next, which is the pointer to the next one. And then you can see that at the end, like 11, the node containing 11 doesn't, it's the end of the list, so it doesn't have something coming after it. And so its next is just going to be set to the null pointer. And I'm going to indicate that with like a little ground symbol, because I don't know, this is ECE. Slides will be released separately on Brightspace. Yes, the lectures, and I will upload the slides. All right. Yeah. Okay. So that's a basic linked list in memory in C, whatever. Optionally, you can also have like a header, right? So I can keep a pointer to the head of the linked list and a pointer to the tail, and I can put these into their own struct. So if I'm ever doing stuff that needs to know where the tail is, or that needs to know where the head is, or that needs to manipulate these, I can just pass that header around to my different functions, and then I can dereference the head pointer to get the first element of the linked list, and so on. It's a data structure. Pretty cool. Okay. Different kinds of linked lists. Instead of just a singly linked that has a next pointer, we can have this thing, have this idea of like a doubly linked list. So for this, every node knows what the next one is and what the previous one is. So here, the previous for the head is going to be null, the next for the tail is going to be null, and then everywhere in between, it's going to have like a next and a previous. So this lets you like iterate backwards and forwards. This is good because it's like, it makes writing certain algorithms a lot easier because you can traverse in either direction and you can kind of like access both neighbors at a time. It is the downsides here are like, number one, you have to keep track of an extra pointer. So if you're limited on like the amount of memory you can use, then maybe that's an issue. Also, it's more bookkeeping. Like if I want to insert something, I can't just insert it. I can't just have like the next things point correctly. I have to have the next and the previous things point correctly. So it makes some things easier, some things harder. Whatever. It's an option available to you, doubly linked lists. The other thing is circularly linked lists. So instead of having the tail point to null, the tail points back to the head. In particular, this means that there is no like well-defined beginning or end. You can sort of think of any node as like the head of the list, and you just kind of keep iterating around and you get this like circular thing. Again, these are useful for certain algorithms. Sometimes these are the semantics that you want. Okay, linked list basics. Operations that we can do on linked lists. So can support inserting at the head of a linked list. So some pseudocode for that. If I take my linked list header, which has like a pointer to the head and the tail, and the new node that I assume I've already allocated and set up and everything, First thing I do is I set the next pointer of that new node to the current head of my linked list, and then I update what the head points to. Right. Now the arrows are kind of crisscrossing all over the place, but maybe you can like mentally rearrange this to put new node at the left and convince yourself that this is in fact a valid linked list with two at the beginning or a two at the head. So we can insert at the head. We can also insert at the tail. So similarly, this is where the header is useful, right? Because now I don't have to iterate through the whole linked list to find the tail. I can just dereference header.tail. I set its next pointer to the new node. I make sure that the new node is pointing to null so that it's correctly marking the end of the list. And then I update what the tail of the list is. So again, maybe you can convince yourself that that is correct. If we can insert at the head and the tail, we can also insert somewhere in the middle. So here, if I know the nodes before and after, like if I know the node between the two nodes between which I want to insert the new node, this becomes pretty easy. I can before.next equals new node.next equals after. And that works. Kind of. I'm lying to you, but we will get back to that. More operations. Delete. If I want to delete the head, I grab the one that I want to delete. I increment what the head points to, and then I make sure to free it. If I want to delete the tail, this becomes a little bit trickier because I need to know what the new tail is going to be, which means I need to know what came just before the current tail, but my header doesn't point to that. So if I have a singly linked list, I have to, I grab the tail, which I'm going to delete. That's fine. But now I have to iterate through the whole list to find what the node just before the tail is, right? So I have this while loop. I start at the head, and I keep going until the next one isn't the tail, or until the next one is the tail. And so now I know I've found what the new tail should look like. I update header.tail, I update it to point to null, and then I delete the old tail. Okay, and then to delete from the middle, again, I have to do this like loop to find the node right before the one that I'm going to delete. In this case, I didn't want to draw a really big list, so it's just the first one, but you could imagine there being like 100 things before it, and I have to loop a whole bunch of times before I find the 3 that points to the 6. Then I skip over it, and then I delete the one in the middle. So as I sort of alluded to, the loops in delete from middle and delete tail, there's while loops there, those can get very expensive. Right? If the node that I'm trying to delete is at the end of the list, I might have to iterate like 100 times, a million times, right? This might take forever to get to find the one that I care about, which is potentially really bad. So important to know that if you're deleting the tail of a singly linked list, it is potentially very expensive. Fortunately, if we have a doubly linked list, we don't need these for loops, right? Instead of looping to find the previous, I can just say node to delete dot previous, and I can access it directly. So that's good, right? That's an advantage of doubly linked lists. Like I said, the downside of this is now you've got a lot of pointers to manage. You've got a next and a previous. Insertion gets more complicated because now when you insert, you have to like get previous dot next equals this and next dot previous equals this and this dot previous equals previous. Like you have to do all this extra work. It's not impossible. It's not difficult. It's still pretty efficient. It's just more code for you to write. So more chances to mess something up, more difficult to understand the code later. I don't know. It's yeah. Okay, like I said, um, I lied to you earlier. This is the delete from middle pseudocode that I gave you. And it just takes the thing and it skips over it. But there's something wrong here. Does anyone know what's wrong with this? You can feel free to put it in the chat or shout it out. Uh, balance. What do you mean by balance? Oh, so we're not dealing with trees yet. Um, at some point, if we do deal with trees, or like later when we do deal with trees, we will care about like keeping it balanced. Um, could it infinitely loop if node to delete is not in the list? Yes, yes, it could. That is true. That is correct. That's not the thing I was thinking of, but that is essentially that's like morally right. Um, the problem here is what if the node I'm deleting, what if I call delete from middle, but the node I'm deleting is actually the head of the list, right? Uh, so what happens here is I set previous to head. So previous is already node to delete, which means previous.next is never going to be node to delete, which means this is going to loop infinitely, even if this should theoretically be a correct operation. Um, so in particular, uh, yeah, if the node to delete is the tail, it'll work because it'll like go up to the tail, but it won't update header.head or header.tail. Um, so and actually that's also a problem with our inserts, right? If I scroll back, uh, yeah, okay. So like insert it in the middle. Although I guess for this one, I'm assuming that you have the before and an after. But like in general, if you try to just like insert a node into the list, if you happen to insert it at the head, but you didn't know a priori that you were going to be inserting it at the head, um, you won't by default update the like header dot head. And so in the real world, you also have to like add checks to make sure that that's what you're doing and make sure that you update the right things. Also, a lot of this fails to work if your list is empty, right? Like header.head might be null, in which case, well, insert, that's probably fine. But if you're inserting at the tail, header.tail is null. Now you're doing tail.next. You're dereferencing a null pointer. That's bad, right? There's a bunch of like edge cases that the pseudocode does not account for. So when you're implementing your own linked lists, do not just like transpile this into C. There are a bunch of other edge cases that you'll need to think about. There we go. Okay. Um, so one way to sort of solve this like special casing thing is this idea of a doubly linked list with a sentinel. So this is kind of just combining a bunch of stuff that we've already talked about. So instead of using a null value to mark both ends, uh, wrap, we make it a circularly linked list, and so we wrap it around. And then instead of null, it's going to be an actual like dummy node. Um, so the like tail.previous, or sorry, head.previous is going to be the same thing as tail.next, and that's going to be like some kind of like sentinel value. And our linked list header is just going to point to that. Um, and it turns out that if I'm doing this, if I insert before the head, it's still like it ends up inserting. I don't know. Can you see the pointer, the mouse pointer? If I move it here, maybe not. Okay, I'll need to figure out something about that. But anyway, if I insert before 6, I don't have to do anything special to like update head, right? Because it's going to insert between the green dummy node and 6, which means that if I look at head, that's going to be header node dot next, and that'll be the head correctly, no matter what. And if I look at the tail, if I try to insert something like after 1, it's going to insert it between the 1 and the green, which means if I look at like green dot previous, it's going to get me the correct tail no matter what. And I don't have to worry about like null pointer dereferences because there aren't any null pointers. Like everything points to something valid. Um, so this is more complicated, right? It's more things to keep track of, more like semantics that you have to keep in your mind. Um, but it is a cool way of dealing with that. That happens to be all I have about linked lists. We are going through this pretty fast. Are there questions about linked lists? That was the first bit of like actual content. So cool, cool, cool. All right.
Wait, I do have one random question. It's probably not that
Yes.
important, but can you like kind of overview of just like how would you like sort a link list, like a bubble sort link list?
Oh, yeah. Good point. So I can share again. We can take a look at like a picture of a linked list. Okay, so if I've got, well, this is sorted, so maybe that's a bad example. Whatever. Right, okay. So the thing you need for a bubble sort is the ability to iterate through something, right? Which is, we'll talk about, well, we won't talk about bubble sort. We'll talk about sorting linked lists in a couple of weeks. But briefly, you need to be able to iterate through the linked list, which is easy enough. You don't have random access, but that's okay, because for a bubble sort, you're just iterating through the entire thing. So you don't really care what index it's at. And then you need to be able to swap. Now, swapping two nodes is something that you can do, right? Like you get the previous pointers of both of those nodes and you like make their next pointers point to each other, and then you make the next pointers point to, like, you sort of update all of the pointers so that the linked list ends up, so that the nodes end up swapped, right? So you kind of get this like convoluted, tangled mess of pointers going all over the place, but these might be anywhere in memory anyway, so it doesn't really matter. Yeah, so for bubble sort, that's all you need is the ability to swap. Actually, I think a lot of sorting algorithms you can write that way. Something like insertion sort, I guess you just kind of iterate through the list and then find the right place to insert it and then insert it between those two nodes. So a lot of things that you can do with arrays, actually pretty much everything you can do with arrays, you can adapt to be an algorithm that works correctly over linked lists. Sometimes it'll be faster, sometimes it'll be slower. And so it's kind of a matter of knowing what it is you're trying to do, and based on that, whether a linked list is a good data structure to use. Does that answer your question?
Yeah, for the most part. Thank you.
Cool. And yeah, like I said, we'll talk about this more week 3, which is hopefully when we cover sorting algorithms. Oh shoot, I forgot to mention, I'm not going to be here that week. I am going to be out of town at a conference. So I'm going to be pre-recording lectures for that week. So insofar as attendance is a thing for this class, there's no attendance going to be taken that week. There's not going to be any like attendance polls. Obviously, I'm just going to post some videos to Brightspace. I do encourage you to watch those like in a timely manner. And I'll be available via like email and Piazza and stuff like that if there's questions. But I meant to say that at the beginning and I forgot. So, all right. Any other linked list related questions before we move on? All right. In that case, I will start lecture 3. You're all dying to know what lecture 3 is. I'm sure it's stacks. All right. Our first like data structure with semantics, I guess. Oh yeah, a lot of these slides I made these slides myself for the most part, but a lot of them are kind of like reusing content from previous offerings of this course, in particular Professor Jones and Professor Ko from last spring. So if you see some of the like figures or if you see like similarities there, that's why. All right, stacks. A stack is an ordered collection where elements can only be inserted or removed at one end. That end is called the top of the stack. Sometimes you'll see stacks referred to as last in, first out, LIFO, LIFO, whatever. That's because the last element that you insert is the first element that you remove, right? So if I insert something at the top, that is now the element at the top, which means if I remove something from the top, it's the one that I just inserted. And I have to remove that before I can remove the one I inserted before that. So yeah, last in, first out. Examples of stacks in the real world. Function call frames, right? So if we know a little bit about the like x86 execution model or whatever, the most recently called function is the first one that returns, right? If foo calls bar, which calls baz, then the first thing that returns is Baz, and then bar returns, and then foo returns back to main or whatever, right? So you can think of like function calls as existing on a stack, and every time you call a function, you put that function at the top of the stack, and when that function returns, it gets popped off. We'll make that precise in a little bit, but that is essentially how it works. That should say a stack of chairs, not a stack of chairs. But a stack of chairs is a stack, right? You can only pick up the top chair. The last chair that you put on top is the first one that you take off, right? This maybe justifies why it's called a stack, because it kind of behaves like we think of stacks in real life. Okay. Maybe it's important to also point out that stacks are not like linked lists are a data structure in the sense that we had like a struct and we had like specific operations and like a specific way to implement this, and then like different things that you could put on top of it. Stacks are like an abstract kind of data structure. They're like maybe an adapter over a container or something like that, in the sense that you can kind of stacks are things that support a particular set of operations with a particular set of semantics, is what I'll say. Let's talk about the operations. Like I said, push, right? So you can push an element onto the stack. This inserts an element at the top of the stack. This has to make sure that the stack doesn't overflow, or if the stack overflows, you have to do some kind of resizing, or if you can't resize, then it fails. That's push. The inverse of push is pop. So pop removes and returns the element at the top of the stack. For pop, we have to worry about what happens if the stack is empty, because then there isn't an element at the top, and so we have to do something about that. I will talk about that probably not today, but at the end of this lecture, which will be probably tomorrow. And then we've got peek, which returns the element at the top of the stack without removing it. And again, we have to deal with what happens if the stack is empty. So these are like the basic operations that stacks need to support. And these are kind of the semantics, right? So if you push and then pop, you should get back the same element. If you push into an empty stack, it shouldn't be empty anymore. Stacks are not a particular implementation. There are, however, many different ways to concretely implement a stack. The one is linked lists, right? So if you implement a linked list, or if you define like a linked list type or something like that, you can use that type as a stack. To push, you insert at the head. To pop, you delete at the head, right? So the head is now the top of the stack. To peek, you dereference the value at the head. Hopefully it's pretty straightforward. You can also, if you want to use an array, you can use an array as a stack. So here you pre-allocate a block of memory. You have to pick a size of memory to allocate, and you keep a pointer, like an index or whatever, to the current top. We're going to call that the stack pointer. So to push, you write the value to the array at the stack pointer, and then you increment the stack pointer by 1. To pop, you decrement the stack pointer to get back to the top, and then you return the value at that index. And to peek, you just return array as stack pointer -1. If we think about some details of these concrete implementations, can inserting at the head of a linked list, if that's what push looks like for a linked list, can this stack overflow? Do we ever run into a situation where like we push too many elements and the stack overflows and you have to deal with that somehow? All right, I see a no in the chat. Do people agree or do people disagree? Feel free to fight it out. All right, we've got one person agreeing. Cool. Okay, that is like mostly correct, right? There aren't normal circumstances in which the stack would overflow. But of course, we could run out of memory, right? We could allocate like multiple gigabytes of worth of linked list nodes, and then the OS, when we malloc again, the OS says, "Yeah, sorry, I can't give you anything else," and so malloc returns null, and so the stack overflows. Of course, in situations like that, there's not really anything to do about it. So, yeah, morally speaking, in normal operation, that stack shouldn't overflow. What about underflow? If I pop from the stack by deleting the head, but the stack is empty or there isn't something there, can the stack underflow? Yes, yes, it can if it's empty. Excellent. If the list is empty, we probably end up dereferencing null somehow because we're deleting something at the head, but the head we expect to not be null. Um, and this will probably segfault. All right, what about for arrays? Can our array implementation of a stack overflow? I see a yes. I see a bunch of yeses. Hell yeah. All right, that's correct. Once the array is full, the stack pointer will point past the end. Exactly, yes, based on the buffer size, right? So if I've pre-allocated 10 elements, even if I've got a whole bunch of extra memory available, if I've pre-allocated a block of 10 elements, then as soon as I try to push the 11th element, it's going to overflow. It's going to try to write to something that I haven't allocated. And it's going to give me some kind of undefined behavior. So yes, array-based stacks can overflow a lot more easily. Kind of alluded to already, but can this underflow? Yep, yeah, it can underflow, right? If the array is empty, then the stack pointer points to the first element, or stack pointer 0 or whatever. If I decrement it, now it's -1. Now it's pointing past the beginning of the array, like before the beginning of the array. So again, it's going to be dereferencing memory that I haven't allocated. So yeah. I think this might be a good place to stop because there's like 3 minutes left in class, and I don't want to start an example and then stop the example halfway through and then pick it up again. So, um, yeah, cool. Thanks for showing up. Uh, Questions, comments, concerns, anything?
I have a quick one, if you don't mind.
Yep.
So in memory, when you when you're underflowing, are you just going back to like the memory location before like this, for example, the array? Like let's
Mhm.
say the array is at 500, where it just goes like 499.
Yeah, yeah, that
Okay,
is
okay.
in that particular implementation, that's what would happen. Um, if you happen to have something allocated there, it might return that. It might return some garbage things. It might, the OS might stop you from making that like pointer dereference or stop you from making that access. Anything could happen, but it's not good, right? It's not expected behavior.
Thank you.
Cool. Other questions? All right. Well, if there's nothing else, thanks for showing up. I will post the recording and the slides, including probably all of the stacks lectures, so you can like look ahead, get some spoilers there. Yeah, I'll post all of that stuff hopefully shortly after class is over, and I will see everyone tomorrow, bright and early in the morning. All right. Goodbye.